All right, guys, welcome to today's lesson on reaction rates. We're just talking about speeds of reaction, right? You guys should know reactions. Some reactions go slow, some go fast, and we're going to look at various factors that can affect that. For that, somebody sent me an email, recent driver awards. So I think she was at number like 6, or this one was in at number 5. This one somehow ended up on the railroad tracks. Don't know how they got done park. Well, I know how they parked. You know what it was. They got there before all the people got to work, and they just parked however they wanted, and everybody else parked in the stalls like you're expecting. Now that person has to try to get out. That person didn't do too well. You guys ever seen someone like take off with the gas pump at a gas station? Cop rolled up into wet concrete. That is not cool. I don't know how that happened. You guys see how she's got her helmet backward? Her helmet should be like that. And I think she took the award. She was numero uno. Anyways, got a little mathematical puzzle for you. How can you make the following equation here true by just adding one line? If I were you guys, I would just pause it, because I'm going to show it right now. I would pause it and try to figure it out. What could you do? I know what some people want to say. They're like, 2 plus 1 plus 3 does not equal 244. Okay, but that would be the easiest way to do it. Here's another way you can do it. 2 plus 1 plus 3 equals, check this out, guys, look. Isn't that the divide sign? What's 24 divided by 4? 6. 2 plus 1 plus 3 is 6. You know what? I was even thinking of another thing we could do. Check this out, guys. This is what Mr. Wilson thought about himself. Check this out. One line, one line. I just made that plus a 4. 241 plus 3, 244, baby. All right. Let's move on. Now we're getting to our topic for the day. Kinetics has to do with reaction rates. Kinetic, right? Movement, right? Molecules are moving, they're colliding. Some bonds can be broken. The faster those bonds are broken, new bonds form, the faster is the reaction. Reaction rates, how fast does it happen? And that's determined experimentally. So we could actually measure the rate at which, it's really, this is what you would be measuring, the rate at which there's a decrease in the concentration of reactants over time, or an increase in the concentration of products over time. So you can always look at a reaction speed either from the perspective of the reactants or the products. So with that, so you guys write that down. We could look at let's say we wanted to collect, right? You guys, whenever you have something in brackets, that's concentration. So I'd read this as the concentration of reactants over time. So think about it. If you have a reaction that's progressing, and you were measuring the concentration of the reactants over various times throughout that reaction, what do you guys think a curve of that data would look like? You guys should think, if you're going from reactants, right, R, to products, what's happening to the concentration of reactants as the reaction is progressing? Isn't it decreasing? You guys would actually, and you're going to get a smooth line. It won't necessarily be a straight line. It'll be a smooth line. But what you'll expect is you'll expect it to look kind of like this. I know if you guys were predicting it go down, that's good. But you guys notice why you would have a curve like this? Because you guys look, initially when the reaction first starts, right at the beginning, you see how the concentration of reactants is going to drop very, very quickly. Why is that? Because at higher concentrations, right, wouldn't you expect there to be a lot more collisions between those molecules, and thus you would expect the rate of the reaction to be really quick at first, and then you can see it begins to slow down. And why would it slow down? Because, right, as the reaction progresses, you're having less and less reactants that can collide together in order to form products. Now, if we wanted to look at it, a reaction rate from the perspective of the products, you think about, what do you think that curve might look like? This was from the reactants, this is the products. Those of you guys who were thinking it would go up, that's correct, but more specifically, it would look like this. And so it is increasing, but now what you'll notice is you'll typically have a curve like this, because what do we see? At the beginning of the reaction, the increase in the amount of products is very dramatic. That indicates that the reaction rate is very quick at that point. And why is that? For the same reason that there was a dramatic decrease in the reactants at the beginning. So what happens to the reactants? They become products. So with a dramatic decrease in the concentration of reactants, there's a corresponding dramatic increase in the concentration of products. And then you see the concentration of the products begins to, you still have an increase in the production of products, but it begins to slow as the reactants are used up. All right. So collision theory, I kind of already made mention of that. The theory is that in order to react, molecules must collide. They have to come in physical contact with each other. So if that's the case, the rate of a reaction, how fast a reaction happens, is going to depend on the number of collisions per time. Wouldn't you guys agree? If you have more collisions between molecules, therefore when you imagine you would have an increase in the reaction rate. But there's also another factor, the percentage of collisions that are effective. Because just because molecules collide doesn't necessarily mean they're going to effectively react. So let's look at an example of that.
For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting.
So that would be an example of a collision. They came in contact with each other, but there was no rearrangement of atoms, and therefore it was an ineffective collision. If you heard her, it's because, let's say they didn't collide with enough energy. Because what do you have to have energy in order to do what? Don't you have to break existing bonds first? And those have a certain amount of bond energy. If they don't collide with an energy at least the bond equivalent to the bond energy of the existing bonds, then those bonds are just going to stay intact.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
So they're bringing up a different situation. In this case, they did have enough energy, but they didn't have the proper orientation. So molecules also have to collide with the certain atoms colliding with certain atoms. So now let's look at a case where both of those are true.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
See how we ended up with a different rearrangement of atoms? These are different products. So now we have the products. This was an example of an effective collision. And so just imagine that happening on the order of trillions and trillions of molecules, even in a small sample of matter. If you increase the frequency of collisions, or the percentage of collisions that are effective, what's going to be the result? You're going to have a faster reaction rate, because the faster it'll be such that the products are formed. So he's asleep and he wakes up. Dang, I can't stop worrying about getting insomnia. Okay, factors that affect reaction rates, guys. This is kind of the crux of the lesson today. I kind of wanted you guys to pause this and try to think, what do you think, what's the factor you think we could change? And I'm thinking the first one you guys should get. What's a factor that might affect how fast a reaction occurs? What could you change? I think a lot of you guys might guess the temperature. And typically, usually the higher the temperature, the faster the reaction. Let me show you an example of that. Here, I don't know if you guys can see down here, but I have some hydrochloric acid. Okay, that's hydrogen chloride dissolved in water. That's what it is. Okay, so and then what I'm going to do is I'm going to get some zinc. Guys, here's a typical reaction is acids tend to react with metals. So I have this zinc metal. You guys see it's kind of your typical kind of silvery. It's a typical salt, okay? So I'm going to add hydrochloric acid. And if it's just been sitting here, how would you describe the temperature? Wouldn't it be room temperature? So I'm going to add it to the zinc. And typically, what happens with acids when they react with metals, they form hydrogen. You guys should know hydrogen's a gas. So if we knew that, what would we predict to observe if in this chemical reaction? Hydrogen's a gas when you expect to observe bubbles. I don't know if you guys can see it here. You guys should be seeing some bubbles. But you know what? This is not too exciting, because really, if you were to describe this, how would you guys describe the rate of this reaction? When you say it's kind of slow, and I can see that based on just observing the bubbles. The production of bubbles is relatively slow, indicating the reactions are occurring relatively slowly. Okay? So let's do the same thing. So I'm going to get another test tube. I'm going to put some zinc in it. But the only difference here this time is I'm going to take hydrochloric acid that I put on a hot plate. I don't know if you guys can see it. You can probably see it raised. It's actually on a hot plate. So I've been heating this up. So it's So it's at a higher temperature. So then I want you guys to try to predict what do you think is going to be different about this compared to when I had the acid at room temperature. So I put that in there. And hopefully you guys recognize, hopefully you guys can see that bubble production is much more dramatic. Now let me put them side by side. You guys see this was room temperature water. This is the warmer acid. You guys, to kind of further that, you guys might know hydrogen is flammable, okay? So what I'm gonna do is I'm gonna take that room temperature one. You guys see it is generating hydrogen, not very fast. So what I'm gonna do is, you can do what's called a hydrogen test. You can just take a splint. You guys, this is just a wooden splint. I'll light it, okay? And then I'll put it in there, okay? So let's see. You guys see, you don't really get anything happening. You guys heard I said hydrogen is flammable, so maybe you guys were expecting something. I would normally as well, okay? But let's see if there's something different maybe with the one where I'm generating hydrogen more quickly. So here, you guys see the bubble, the reaction's more vigorous, the bubbles are more vigorous. Now let me put this in. You guys hear that? Let's do it again. Let's kind of wait for the hydrogen to build up there, and then I take the flame, put it in there. You guys heard that? So that when you hear that kind of like that popping sound, that's kind of like what you can do. That's pretty typical when you're generating hydrogen gas. So that's actually a test you can use to see if you weren't too sure what kind of gas was being generated. But in this case, you can see hydrogen was being generated a lot more, such that it was very clear that you could see the combustion with that wooden splint. Okay, so the higher the temperature, generally the faster the reaction. Now, if you think about it, why would that make sense? We just said for a reaction to occur, what has to happen? Molecules need to collide. Well, at higher temperatures, what can we say about the molecules? Aren't the molecules moving a lot faster? Like in this case, the hydrogen chloride molecules are moving a lot faster, and therefore, what are they going to do? They're going to collide with the zinc a lot more frequently. So if they're going to collide more frequently, when you guys expect an increase in the reaction rate? And not only that, when they do collide, if they're moving faster, they're going to collide with more force, and thus with more energy. And so therefore, you're going to have a greater percentage of those collisions end up being effective, which also contributes to the faster reaction rate. Okay, hoping you guys can think of another factor that might think about solutions. What can change from solution to solution? The concentration. So when we talk about concentration, we're talking about for aqueous solutions, those are things that are dissolved in water, and then also gases. You could talk about the concentration of gases. So once again, just make a note, guys, whenever you put something in brackets, that's just an easy way to say concentration. So rather than writing concentration, I would take something, I'd put it in brackets, and it's just known it's concentration. You remember our typical concentration unit is molarity, moles per liter. So when you see that, that's, you notice I put it for the reactants and the products. Okay, so we've got concentration. Let's look at that. You guys, something pretty similar to what we've already observed, but nonetheless, just so you guys can observe it. Let's say I've got also acid. I got low concentration, so I don't have much hydrogen chloride dissolved in this water. Okay, so once again, I'm going to put zinc, and then we'll have a low concentration hydrogen chloride. And as you guys might expect, right? Once again, with acids, I say they typically react with metals to form hydrogen gas. So we are seeing bubbles. I don't know if you guys can see that. It's not happening very fast, which probably shouldn't be very surprising, because what we're saying is if that hydrochloric acid is low concentration, there's relatively little hydrogen chloride in here for the volume that's there. Therefore, if there's less of that within a certain volume, wouldn't you guys expect less collisions with the zinc atoms there in the zinc, and thus a slower reaction rate? So then we compare that to, we'll just do the same thing, but with, I'm sure you guys kind of see where I'm going with this, with, so I'll put zinc here, but this time we'll do it with a high concentration of hydrochloric acid. So there's more hydrogen chloride in for every given volume. We put there, and in typical fashion, once again, we see bubbles, and you should be seeing it happen at a much faster rate than you did with the low concentration. All right. Okay, a third one. Oh, before that. Yeah, what do you want, kid? He says, my frisbee landed on your roof. Tough toenails, it's my roof, so it's not my frisbee. That's kind of messed up. the kid says, well, my dad is the president of the bank that owns this house. So I'll take the Frisbee and your TV too. Man, that kid is pretty bold. All right, you guys, a third factor that can affect the rate of a reaction is surface area. Notice it has an S, that refers to solids. You guys think about it, when you go camping, you don't have to be a Boy Scout or Girl Scout to know when you go camping. Obviously, you guys know the first thing is, let's say you guys got lost in the wilderness, first thing is you got to worry about shelter, right? And then what would be the thing you'd want to do right before even food or water? You'd probably want to build, it's getting cold outside, you want to build yourself a fire. And you guys should know, if you guys are going to build a fire, obviously you're going to need some wood, and let's say you have some matches or something. Would you guys just cut down a big old piece of, like a big old log, saying, hey man, I need a lot of wood? Would you guys cut a big old thick log and then take a match and then try to light that? You guys kind of already anticipate what would happen. You'd have your match, and it would really suck if you were down to your last match and you lit that match and you put it, and where would you put it? You guys know you wouldn't light anything. You guys know when you light stuff, like when I'm lighting like a splint, right? You guys see what'll happen? Look, if I light my splint and I keep it like this, what do you guys think is going to happen to the flame? Okay, maybe it won't so much. Okay, but sometimes, now that this wood is pretty flammable, but sometimes what'll happen to the fire? It'll go out. Why it'll go out? Because doesn't heat rise? So if you want this thing to continue to burn, what would you do? When you light the bottom of it, and then the thing will just continue to burn, right? Because the heat that's generated from the flame will come in contact with the wood and thus continue the reaction. Because once again, guys, what does wood react with? Don't say fire. You guys remember, wood reacts with oxygen. So all I did was just kind of initiate it. Notice I don't have to do this anymore. It's an exothermic reaction. It needs heat. You guys remember why we often need heat? Because you remember we were talking about, don't you have to break old bonds first? But with an exothermic reaction, it's generating enough heat so it can continue on its own. But when you guys go camping, you're not going to take a big log and then light, right? You would probably do the bottom, but you guys know what's going to happen. When your match go out and the log's not going to burn, you guys think about it. What do you need to do? What's wrong with that scenario? What's wrong with that scenario of having a big old log and trying to light it? Let's say I got my flame down here on my match. You guys know what you do. You wouldn't do a big old log. What would you do? You'd break it up. You'd find twigs and sticks, right? And then you light it, and then you would probably get the flame that might even be able to keep you alive. You guys think about it. What's really the only difference between the big log and what you call kindling? Let's say you have the same amount of wood. You know the difference is? It's the surface area. That's the difference. You guys think about it. Which one has more surface area? Wouldn't it be if I took the wood and I broke it up into small pieces? This has more surface area. What do we mean by surface area? Just like the term implies, it's the area of the surface. When you have a big log like this, you think about it. Once again, what does the wood react with? It reacts with oxygen. So what's the only part of the big log that can come in contact with oxygen? Wouldn't it just be the surface, right? So what you do is you break it up, we increase the surface area. So now what you're doing is you're exposing a lot more of the wood to the oxygen. And what's the effect? You're going to have a lot greater increase in the frequency of collisions. So now the oxygen can collide more frequently with more of the wood, simultaneously generating enough heat to kind of get it going. And then once you got enough, then it'll just perpetuate and you just keep putting more wood on, obviously to get that flame going. So surface area, and you guys see where that applies when we're talking about solids. Okay, almost done here, guys. Those are the main ones. Here's one, catalyst. So oftentimes if you want to increase the rate of a reaction, you can add what's called a catalyst. And in a reaction, like this would be a typical reaction of the decomposition of hydrogen peroxide into water and oxygen. If we wanted to add the catalyst, if you want to show that in the equation, you typically put it over the arrow. We're going to talk about that in another lesson, but catalysts typically increase the rate of a reaction. And then lastly, I just kind of put it bigger in case you had a hard time seeing it. And then the last one is simply the nature of the reactants. You guys, the reality is some reactions are slow and some are fast. You think about it, what would cause a reaction to be just slow? Wouldn't you guys agree if it has very strong bonds between the atoms? Because if it has really strong bonds between the atoms, wouldn't you guys agree it's going to take a lot more energy in order to break those bonds, separate out those atoms? The more energy required, you would agree, if you're talking trillions and trillions of molecules, the less likely that when molecules collide, they're going to have the necessary energy in order to overcome that the strength of the bonds holding the atoms initially together, and therefore it's going to be a slower reaction. You can imagine some reactants simply consist of atoms that have weak bonds between each other, therefore weak bonds indicating easier to break up. Therefore, when molecules in that situation collide, there's going to be a greater percentage of them are going to have the necessary energy to overcome the relatively weak or low bond energy between the atoms. Therefore, you expect a faster reaction rate. All right, guys, that's all I got today. Until next time.